Today we have Rodrigo Fernandez speaking on mass ejection, compact objects, and EM transients. He is a former grad student right here at CITA. He's a former student of responsibilities. Then went on to a postdoc at the Institute for Advanced Studies at Princeton, and then spent a few years at UC Berkeley. And he is now a faculty member at the University of Alberta.
All right, thank you for the introduction and thank you for the invitation to come. It's glad to be back after many years. It's always happy to be back in Toronto. So today I'm going to talk about ways in which mass ejection from the vicinity of compact objects can result in electromagnetic transients. Okay, and you see the picture of the electromagnetic counterpart of the recent LIGO detection here. So it's kind of hinting at where I'm going. And so just the structure very briefly, I'm going to review generally how we can relate mass ejection to electromagnetic transients. That's just the basic physics to set the discussion. And then I'm going to talk about two specific cases. One is mass ejection from the accretion disks that form in neutron star mergers. And then I'm going to talk about mass ejection from core collapse supernovae that fail to explode in the traditional sense. Okay, yet they can still eject some interesting amount of mass that can give rise to electromagnetic transients. So the motivation, of course, is predicting the properties of electromagnetic transients, given that there are now so many surveys operating and some even coming up in the future, like LSST, which are going to improve our capability of sampling the time domain of astronomy. Okay, new types of transients on short periods of time. And also, of course, follow-up of LIGO sources is a very important application of this. And so beyond just predicting progenitors of specific transients, there are some science applications that can be coming out of the study of transients in of themselves. For instance, the origin of chemical elements, you know the R process for the case of neutron star mergers, but core collapse supernovae and type 1a supernova and other types of transients also generate chemical elements that are of interest. There are probes of fundamental physics associated with them, such as the equation of state of dense matter, or even probes of GR in the case of mergers of compact objects. Compact object formation, I already mentioned core collapse supernova that can give rise to either neutron stars or black holes, and other astrophysics, as I said, for instance, just knowing what the progenitors are of unusual transients that might be detected by these surveys that are in operation at the moment. Now, a large class of transients, not all transients, but a large class of transients are related to the ejection of mass, okay, and binding of mass from a gravitational potential, okay, and in particular in the vicinity of a compact object potential, okay. And so essentially, if you want to eject mass that is gravitationally bound to a compact object, you have to add extra energy. So there are physical processes operating that transfer or generate energy to make this ejection happen. And so in most cases, this ejecta that's being unbound from the potential initially is such that the photon diffusion time is long compared to the expansion time. Okay, so the time it takes the radius of this ejecta with the characteristic size to double, okay, in time is much shorter than the diffusion time. So radiation and therefore the internal energy that is initially accompanying this ejecta is trapped, okay? But after sufficient expansion, the density drops to the point at which the diffusion time becomes fast enough that most photons can leak out, okay? And there you have a peak in the brightness of this transient, and therefore it's when these are most likely to be detected, okay? Now, after this initial spike of radiation, if nothing else goes on, the emission just decays and that's the end of it. But if there are further sources of energy, such as radioactive decay from nickel-56 in the case of type 1a supernova, or R process radioactive decay, then this transient can continue in time and will have a slightly different time dependence. And The order of magnitude way of thinking about this was first formulated by Dave Arnett in 1980, basically stating that the time at which this transient peaks is given by the equality between the diffusion time, okay? That depends on essentially the characteristic radius of the ejecta times the diffusion coefficient, which is just dependent on the opacity, okay? And the expansion velocity, which says the expansion time. So you get an expression that depends on the square root of the mass, the opacity, and inverse square root of the velocity, okay? That's just to set the stage. And you can understand type 1a supernova, core collapse supernova, kilonova in the case of neutron star mergers with that general formalism. Now, there are subtleties associated with that. It's not just so simple. For instance, this estimate was derived for a constant opacity. In the case of a core collapse supernova, what happens is that when you eject the hydrogen envelope, say, of a massive star, and a shock runs through it, it is all ionized, okay? And the opacity is high. But once the ejecta cools down, there's a recombination front coming in from the outside in. And at that recombination front, the opacity drops, okay? And so that's what sets the photosphere of this expanding ejecta. And so it's slightly more complex than just a single number. But the essence of it is captured by this argument, okay? So that's just the basics that I wanted to establish, in case you haven't seen this kind of physics before. All right, so moving to the first application, neutron star mergers, and given that so much of the recent detection happened here at CITA, I'm not going to repeat everything that's being said. I know that you already had two talks on neutron star mergers and ejecta and transients already by David Radice and Brian Metzger. So I'm just going to give you a very brief overview just to remind you of what the theoretical issues are. And then we're going to go on to discuss mass ejection from the disk. And so neutron star mergers emit electromagnetic radiation over a broad range of timescales and wavelengths, okay? Depending on the different phases of the merger, here we have early high energy emission and subsequently emission at ever increasing longer wavelengths associated with, for instance, the onset of a jet, if there's any, around the compact object, mass ejection from a disk or from the collision itself, and then the synthesis of our process elements, and then the radioactive decay of these elements as the ejecta expands, giving rise to a kilonova transient or a radio transient at late times once that ejecta collides with the interstellar medium. Now, traditionally, the ejecta coming out of this event is the so-called dynamical ejecta. Okay, this essentially is material that is unbound on the dynamical time by tidal forces and just the collision between the two neutron stars, and leaves the system on a time scale of milliseconds. Okay, and because it is so fast, okay, it preserves largely the composition that the neutron stars had initially, which is essentially all neutrons and a few % protons, okay? And that material is just launched far away from the merger on very short timescales. And neutrinos, which are the real entity that can change the composition, neutrinos don't have time to do any alteration, any significant alteration to most of the ejecta. Some of it coming out of the polar region is expected to be affected. That's work in progress. Simulations are increasing the realism with which they can capture this effect, but till now it's emerging as maybe there's some reprocessing going on along the pole. But most of the equatorial dynamical ejecta is pretty much very neutron rich and remembers the neutron star composition. Okay. You might also remember that when the ejecta is very neutron rich and you get to make heavier process elements, the opacity, okay, in the optical band is extremely high, because all those atoms have a large number of lines, okay, that essentially blanket the optical band. And so most of the light ends up coming out in the infrared. Okay? There's an early blue component because at the beginning the photospheric radius is small and the temperature is high, but as the ejecta becomes transparent, most of the energy of that very neutron-rich ejecta comes out in the infrared. And so, and that's to be expected from some very basic physical arguments about the atomic structure of this nuclei. Okay, so that's why this paper we did a little review with Brian Metzger a while ago. It was printed in 2016, so okay, a year before the transient, and we had no doubt that a red kilonova would be seen because there are many arguments in favor. We didn't know about the blue kilonova or the neutron precursor because, as I'll explain, whether it happens out of the disk ejecta depends on a number of more complicated physical effects. Okay? But to summarize, the dynamical ejecta is very neutron-rich, leaves the system very quickly, and that ejecta was known to exist for a very, very long time. Even Latimer and Schramm, 1974, the ones who first wrote the paper that hypothesized that the R process would come out of this event, were thinking about the dynamical ejecta. Okay? Now, in addition to the dynamical ejecta, as we will see, there's also an accretion disk that forms. Okay, so this will be the dynamical ejecta, and this is an accretion disk that is made up of material that is gravitationally bound. Okay, so it cannot escape, but it has sufficient angular momentum that it does not collapse to the black hole right away. Okay, so it's rotationally supported. And that disk subsequently evolves on a longer time scale compared to the dynamical time, okay, where other processes can take place, including irradiation by neutrinos that can change the relative numbers of neutrons and protons, and therefore change the subsequent composition of the ejecta. And just for the sake of explanation, this is what we call the dynamical ejecta. This is the central object, that in this case is a black hole, and this is the accretion disk formed in the merger. And of course, we expect that in some cases, maybe all, we don't know yet, a relativistic jet should also come out of here. But that's also work in progress that we expect, hopefully, to answer in the next 5 to 10 years if we're lucky with our simulations. But the point is that ejecta coming from the disk was not known to exist as a significant contributor 10 years ago. Okay? It was thought that, yes, that this disk eject mass, but the quantification of how much and what kind of composition is only relatively recent in terms of our understanding of it. So there was early work by Brian Metzger looking at the long-term evolution of this accretion disk and how the viscous evolution, now when angular momentum is transported on the disk, can lead to essentially some mass ejection at late times. Okay? And just to clarify here, the relevant time scales in the system are the orbital time, which is essentially the dynamical time on a time scale of a neutron star is about 3 milliseconds, slightly larger radius, 50 kilometers. The viscous time, of course, is dependent on what you assume by an equivalent alpha parameter, but if it's 0.03, say, it's about 1 second, okay, 300 milliseconds to 1 second. And the thermal time, which is related, for instance, to the total internal energy divided by the neutrino luminosity, is about 30 milliseconds. So it's a hierarchy of timescales that determine the evolution of the system. Okay? And so initially, once formed, this disk is very hot, and hot compared to the gravitational potential of the system. It could also be degenerate, so that's why it's not trivial that it's hot. It's just because there are shocks taking place at the merger. And the temperatures are about 5 MeV, and densities of order 10 to the 10, 10 to the 11 grams per cubic centimeter. Okay? And under those conditions, neutrino emission is very significant. Okay? And so the main coolant of these accretion disks at early time are neutrinos. Okay, the optical depth to photons is about 10 to the 20. Okay, so they're completely trapped in the system.
The dominant emission mechanism is Hooker process?
Yeah. So charge current capture or emission. And you have neutrinos and antineutrinos. So the ratio of electrons to neutrons or the protons to neutrons can vary depending on the temperature and the density. Okay. And so now, as the disk spreads out viscously, eventually these weak interactions shut down. Okay, and the disk turns into what is called an advective accretion disk. So there's no cooling in the system. So there's viscous heating. Okay, be it by the MRI or by some other process, but the MRI is the primary mechanism, but there's no cooling. Okay, there's expected to be a significant outflow coming out from the disk, and this outflow is not just because viscous heating is injecting energy, but also because there's nuclear recombination taking place. And what is that? So at those temperatures I mentioned initially, 5 MeV, 10 to the 11 grams per cubic centimeter, that's so high that nuclei cannot exist. Okay, they're completely dissociated into neutrons and protons. Okay, but once the disk expands and cools, okay, the recombination of those nucleons into alpha particles and then heavier nuclei becomes possible. And just as is the case in stars, for instance, when you recombine hydrogen, you release the binding energy of the hydrogen into the ambient. Here, you release the binding energy of those nuclei. Okay? So that's what it means by nuclear recombination heating. Also, there's neutrino heating. Similar to core collapse supernova, the luminosities initially are very high, 10 to the 53, 10 to the 52 arcs per second. So some of the neutrinos are captured or absorbed by the matter, and that energy deposition can eject some material and bind it thermally.
Is it clear what the relative amounts in those two channels, the combination heating and the neutrino heating are, the relative yields of mass?
I can give you an empirical answer. If I shut down nuclear recombination in my simulations, I lose like 30% of the mass ejection. You can maybe... Oh, no, neutrino heating, it depends. Neutrino heating, it depends if you have a black hole at the center, it's like 1% of the mass ejection. It's just tiny. If you have a hypermassive neutron star, it's order unity compared to viscous heating. Viscous heating is the dominant, when you have a black hole, is the dominant channel, and then alpha recombination is like 30%, 20%.
You will have an initial phase.
Yes.
So.
But the thing is that in the black hole case is self-irradiation. So the disk emits neutrinos, and those are self-absorbed, so it's much lower. And I'm sure a slide later on. Whereas when you have the hypermassive neutron star, it's like a light bulb at the center. It's just irradiating everything. So. Yes. All right, so this is what we expect theoretically coming in. So now if we want to simulate this is the first time I got into this problem was to simulate this in more than one dimension. One can write the equations that characterize this, and the reason I do this is just to show you what the relevant source terms are and where progress needs to be made to get more believable answers. Okay? Now we're at a stage in which we have a rough sense of how the evolution of the disk should be on long terms. But these are basically the weaknesses that we can improve upon to make a more realistic answer. So if you want to simulate this on a computer, you have to solve mass conservation, momentum conservation, energy conservation, and lepton number conservation, importantly. And this basically tells you the relative abundance of protons and neutrons, which is dependent upon these neutrino interactions with matter. Okay, there's neutrinos and antineutrinos, primarily electron-type neutrinos and antineutrinos, which can convert protons into neutrons and vice versa, and they alter basically the electron fraction, which is a single number that can tell you what the actual composition looks like. And so we have the neutrino terms that affect both lepton number conservation and energy conservation, because there can be heating or cooling depending on the energy loss or gain. There's the angular momentum transport, okay, which can be alpha viscosity if you want to do it in a more simple way, or if you want to do MHD, okay, it's going to affect both the angular momentum and the energy because there's dissipation, so viscous heating in the case of just an alpha heating term, or dissipation of MHD turbulence in the energy equation. And then, of course, gravity. So these are Newtonian equations. If you want to write the minimal model to describe this, you can use a pseudo-Newtonian potential to describe the black hole. It's going to have an ISCO, material is going to go in. But of course, we know general relativity is important, so all these equations can be rewritten in a general relativistic framework, and then, of course, you don't think about the gravitational potential, you think about the metric, okay? But this is all, one can always write this in GR, okay? So these are the basic equations, and so the initial or the minimal model, so to speak, one can use is, as I said, using a pseudo-Newtonian potential, which is just like your Gm over R that you will know, but just add a few terms that give you an ISCO and an accretion onto a black hole, alpha viscosity, a neutrino leakage scheme, which is it's really a trick in which you interpolate between optically thin and optically thick. When it comes to cooling, you just compute the optical depth, and you say, if I'm optically thick, cooling is by diffusion, and if I'm optically thin, I just emit all the neutrinos, and then I just interpolate in between. And to absorb some of the neutrinos, you can use the simplest approximation called the light bulb approximation, which, as the name indicates, is just a light bulb at the center that's radiating neutrinos. Okay, in reality, emission and absorption are coupled, so it's not so simple, but that's a simple initial.
That's the same. Light bulb basically means that you have point source at the center. That's what you're saying.
Yes, not necessarily a point source. There's some finite radius. In case, for instance, if you have a hypermassive neutron star, it's just a sphere. But if you have a disk, you can define it to be a ring at the radius where the emission is maximum. This is not spherical, but just a ring. And I can show you the geometry of the emission afterwards. Okay. Okay, so if we do that, we find that the disk ejects indeed a significant amount of mass. Okay, so this is an animation of the evolution of a disk evolved in 2 dimensions, in hydrodynamics with all the physics I just described. And as I said, when you don't include magnetic fields, once neutrino cooling shuts down, once the disk spreads out, is really when the mass ejection begins. Okay? And under these assumptions, the disk can eject about 10 to 20% of its initial mass. Okay? And the electron fraction is between 0.2 and 0.4, which is neutron rich, so less than 0.5, but not so neutron rich as the dynamical ejecta, which is like a few percent, 5%. Okay, this is less neutron rich. Importantly, the speed is lower, 0.05 c versus 0.1 to 0.3 c. And the reason is that the way ejection really happens is that you first transport angular momentum and move material to larger radii, and then viscous heating unbinds it thermally from that larger radius. Okay, so the escape speed from that radius is smaller than the dynamical ejecta, which really comes from basically the core of the merger. Okay, and so there's a lot more gravitational energy you can tap from when you eject things dynamically.
So here in this calculation, you have a spatially uniform alpha. So there's no complications introduced. Alpha might depend on the position.
No. Yes, I'm not going to show any MHD results because I'm being taped, but the answer is that when you do the MHD, the late time ejection looks very similar to this. Okay, we're missing the polar outflow that you get due to the magnetic stresses, but this late time ADAF phase.
There's a long history of studying such processes in black hole accretion, right?
Yes.
Where a convective flow is pulling energy. So if I create an atmosphere or an extended disk which has a relatively low binding energy, and then I convect out some energy from the interior, right? And it's a small difference between a wind and an even larger atmosphere.
Yeah. Well.
So are you seeing convective energy transported?
Yes. So if you talk about an atmosphere, that means that it's bound. You see? Yeah. So I do see that in this case, not everything is unbound. Some of it is bound, and it just keeps convecting to larger radii, but it stays in the vicinity. And some of it, 70-80% of it, depending on various parameters, it just goes away. And so yes, indeed, you form like an extended puffy atmosphere with time. And just to give you a sense of scale here, 1 unit of orbit is 3 milliseconds, so 1,000 orbits is 3 seconds. Okay, and so you need to evolve this to almost 10 seconds, so 3,000 orbits to really get to converge in mass ejection, which means that you started with a torus, and then most of the material either leaves or accretes, and there's nothing left afterwards. Okay, that's the way to consider this. Okay, so some important dependencies. First of all, the spin of the black hole affects what the composition of your ejection looks like. So this is the wind, a snapshot of the wind in electron fraction. Okay, for a non-spinning black hole and a black hole with spin of 0.8, which is roughly what you expect from two neutron stars of about 1.4 solar masses. And so the electron fraction is higher. And the reason is that as you increase the spin, of course, the ISCO, okay, moves inward. And so the material in the disk can get hotter. And so neutrino rates are much larger, temperature to the 6th power, okay? They're much more powerful to reprocess material, and it tends to get to higher YE because it's less degenerate. Okay, so you have more positrons around that can increase essentially the electron fraction. And just to give you a sense for what's the critical YE one needs to care about, it is about 0.25. Okay? So below 0.25, you make all the heavier process elements, which gives you this lanthanide-rich ejecta that gives you an infrared transient. And above 0.25, you don't make it past the second R process peak. And then you don't make the lanthanides, and you have an opacity that is essentially that of iron-like elements. And so it gives you a blue kilonova. Okay, so that's really where this is really going. Okay, and so this here is time, and this is mass flux, so solar masses per second. So this is the accretion rate at the ISCO. And this is the mass ejection at 10 to the 9 centimeters, which is 10,000 kilometers, essentially. And if you increase the spin, you eject more mass with higher electron fraction. You know, that's one of the basic results of this study, and it's also been done by the Max Planck group with better neutrino transport, but essentially the same result.
Sorry, this is 2D, right?
Yes, 2D. It rotates very rapidly, and so there's no reason.
I'm just worried about the convective energies or whatever.
Yes, I know the turbulence, but it's rotating rapidly, and so it's not quite the same as the free turbulence in non-rotating media. And it turns out, didn't expect that in MHD at late times it looks very similar, pretty axisymmetric. Now, going back to the issue of the light bulb, now if instead of having a black hole at the center, you put a neutron star, okay, with a hard surface and a significant flux with neutrinos, then things change because this is density almost the same, but this is neutrino heating, okay? The amount of neutrino heating when you have a neutron star is significantly higher than when you have the neutrinos only coming out of the disk itself, okay? And neutrino heating is also associated with neutrino absorption, which changes not only the energy, but also the electron fraction. Okay? Viscous heating is not very different. It's just set by the angular momentum of the disk material. But the electron fraction coming out of an accretion disk from a neutron star, or hypermassive neutron star, is significantly higher than that from a black hole accretion disk. And this is really what underlies this claim that given the transient we saw in GW170817 and the blue kilonova, the hypermassive neutron star must have had a finite lifetime. And there was no prompt black hole formation. So this is really, I'm not saying that this is the only reason, but this is the first time that we demonstrated that explicitly. And at the time we were thinking, oh, maybe we can even constrain the lifetime of the neutron star based on the composition. But there are so many complications in the physics that it's very difficult to make a one-to-one mapping. For example, you could also think that the black hole spin can give you higher electron fraction. So it's not a one-to-one mapping. But this is really the main idea underlying the claim that the hypermassive neutron star lived a little bit. Okay. This is also a couple of snapshots from the same paper showing this is a mass histogram. Okay, and this is the electron fraction along equatorial latitudes. Okay, so 60 degrees from the equator, and then polar latitudes. Okay, so 30 degrees from the rotation axis. And so these numbers here are the lifetime of the hypermassive neutron star, after which it becomes a black hole. Okay, so the inner boundary disappears, and the neutrinos from that hypermassive neutron star also go away at that time. And so the longer the lifetime, the more mass we eject, and the higher the average electron fraction is. Okay, the more lanthanide-free ejecta and the more blue kilonova we should have. Okay, this is again the same plot showing you the accretion rate as a function of time and the mass ejection when you collapse the neutron star at different times. Okay. And an important point that hasn't been made yet, or maybe it has been made but not too repeatedly, is that when we carry out the simulations in pure hydrodynamics, okay, there's a maximum velocity that we get, roughly speaking, 0.1 c. And it has to do with how much energy we have to inject from the neutrinos or from the viscous heating given the depth of the potential. And if you remember, the blue kilonova from DW170817 had a velocity of 0.2 to 0.3 c. Okay, it's a factor of 2. I know it's not too much, but it's difficult just with hydrodynamics to reach the velocities of the blue kilonova that was seen. Okay, and so that's where we think that magnetic fields can provide maybe the last little push to get us to where we want to be. All right, now in the opposite direction, so I told you ways to make the ejecta less neutron-rich. These are ways in which it can get more neutron-rich. It turns out that the disk doesn't exist in isolation. There's not just a clean accretion disk and vacuum outside of it that's just ejecting mass, but the dynamical ejecta is not all unbound. Okay. Most of it is going to go away because it just has an energy above the binding energy of the gravitational potential, but some of it is not. Okay, some of it is gravitationally bound, and it actually comes back to the central object. So this is called fallback. Okay, and so the fallback cannot go to the central object unimpeded because on the equatorial plane we have the disk. Okay, so essentially there's an interaction between the fallback from the dynamical ejecta and the disk. And so in this study, what we did is take a merger simulation. It was done in Newtonian gravity by Stefan Rosbach, and map it into our disk evolution code and paint the different components in different colors and see what happens. And of course, you can compute integrals and everything else. And it turns out that for this specific set of parameters, the dynamical ejecta wasn't very massive, and so the disk wind just blew up the fallback. Didn't make any difference. So it shut down the fallback accretion onto the central object, which has implications, by the way, on arguments that there can be a late time powering of the central engine through fallback. Okay, it's not that fallback comes cleanly onto the central object. There's a disk in between that is ejecting mass. Okay. Here we took a different simulation, this time from Francois Foucard, and this is a black hole neutron star simulation, so it's more compact, higher black hole mass, same radius. And so here, these are different snapshots of the evolution. Red is the disk, blue is the fallback. The fallback basically penetrates into the disk and mixes up. Okay. And as I told you, the electron fraction of this material is a few percent. It's very low. Whereas the disk is getting raised by the neutrinos and every other process to 0.2, 0.3. But once the fallback comes in, it mixes up and it lowers it, okay, significantly. So more quantitatively, one can I'm just focus on this plot here. The electron fraction distribution of the disk when evolved alone, just pretend that there's no dynamical ejecta, and the dynamical ejecta itself, assuming that the disk doesn't exist. But when you evolve them combined, the disk, or the material that was in the disk initially, acquires a low YE tail, and the material that was in the fallback essentially gets mixed up. Okay, and you have a wide electron fraction distribution. Okay, the velocity is it's okay. This is the unbound dynamical ejecta, and these are the two, not too different. But this was a pseudo-Newtonian simulation out of a GR simulation, so the velocities are not super reliable.
What's the characteristic time scale for the fallback comeback, or is it a range of time scales?
It's a range of time scales. Some of it comes back.
Power law dependent some time of the fallback accretion rate?
Basically, so you see that it starts falling back on like a few millisecond times, which is the dynamical time at the disk radius, and it keeps coming. Yeah. All right, so one can be more quantitative about the composition, not just talk about the electron fraction and this characteristic value of 0.25. One can actually put tracer particles on the accretion disk, and then use an actual nuclear reaction network on those tracers and the thermodynamic quantities they record, and compute abundances, okay, of our process elements. And as I was telling Chris, the disk is convective, so the trajectories of these particles are not so clean as with the dynamical ejecta. They just leave. Radially here, they do all kinds of weird motions. So sometimes the network has problems because they come back, get heated, they move back and convect and do all kinds of crazy things. But the bottom line, just not to complicate things too much, is that most of the studies that have been done on the disk, including the ones in which I've been a participant, show that, so this is, by the way, this is mass number. So our process elements are from about 90 to all the way to 200, and this is the abundance relative to solar. Most of the studies of the disk ejecta show that light hour process elements are the primary product, with varying amounts of heavier process elements, so that's more than 130 second peak, depending on various things such as the viscosity that one uses for the disk, or the mass of the disk that can change, say, the entropy or some other parameter, thermodynamic variables. But the composition of light hour process elements is pretty robust. So we think that if the blue kilonova is coming from the subrelativistic ejecta, okay, there are claims that it doesn't, that there's the cocoon doing some other things. But if it is from the subrelativistic ejecta, then it's most likely coming from the accretion disk ejecta. This is another study showing what happens when we have a hypermassive neutron star at the center. Essentially, all of the composition is lighter process elements, and even some lighter elements, iron peak here. And then again, we have this very large variability of even more than an order of magnitude in heavier process elements, depending on things like the lifetime of the neutron star. So this is 10 milliseconds, 30 milliseconds, or 300 milliseconds. Infinity means it lives forever. Of course, that may not happen, or very unlikely to happen. But you can still do it in the computer, okay? And you find that it's very low, heavier process elements. And this is a very nice plot that Jonas Lipponer and Luke Roberts put together. One can also use the particles themselves to trace the dynamics, okay, of the outflow. And when we have a hypermassive neutron star disk, they separate into very clean or clear populations depending on the time at which they're ejected. So this early banana here is neutrino-driven, because there's a clean correlation, primarily neutrino-driven, between the entropy and the electron fraction. So you absorb a neutrino, it changes your electron fraction, but also changes your entropy, because you absorb the energy. Okay? So this is a neutrino-driven component, and then at late times, okay, you have this messy convective ARF kind of outflow that covers basically all of parameter space here. Okay? And that's underlying the claim I was making before about neutrino heating versus the viscous.
But there isn't much material there below 0.25.
Below 0.25? You mean here? Yeah, so that's related to the low abundance here. So almost everything is.
So it's not neutron rich enough.
No. Yes. So but you want that to be the case, because you want the blue kilonova. That's really what's.
So there's a bit of a tension here.
In what sense?
If you make the blue kilonova, you may not make enough third peak.
Yes, that's true, because, yeah, that's a very good point. Because given the parameters that were observed and the known equations of state, the dynamical ejecta is actually very little. And so the disk is supposed to dominate the ejecta, and if it's a long-lived hypermassive neutron star, you don't make any third peak elements. That's true. That's true.
So we also had to talk by Nancy. Do you want to say something about the Cocoon model?
Not really. Yes. No, I'm being taped, so it's contentious. All right, so just to wrap up this part of the talk, pending issues before we believe what's coming out of the simulations. Generally, would say I'm confident that we have it to order of magnitude. Okay, but if we want to compare with observations, and the observations are really good, okay, better than anybody expected, so I think the simulations have a lot of catching up to do, we need to include magnetic fields in the evolution of the disk, and this has been started already. Siegel and Metzger have some MHD results, and Nouri et al., they mapped from a merger simulation. That's the SXS collaboration. And we have, in collaboration with Sasha Tchaikovsky and others, MHD models. Now, in those models, we start with an artificial magnetic field, poloidal, just because it's easy and makes everything easier to treat, basically. But in practice, in these mergers, we expect toroidal fields to be formed when you tidally disrupt the neutron stars, and so that makes it harder numerically. And so that hasn't been done yet, and that's future work pending for somebody to do, realistic initial conditions. And also neutrino transport has to be improved in addition to the MHD. Okay? Neutrino transport alone has been done, M1, basically by Just and Fujibayashi. But the composition itself is most sensitive to the neutrino physics. Okay? MHD sets the amount of mass and the velocity, but the composition is just the neutrinos. So if that gets to be improved, then we will believe more what's coming out of this disk outflow simulations. All right, so in the last 10 minutes, I'm going to talk about something completely different. We started talking about mass ejection and transients, and so I'm going to switch to the case of failed core collapse supernova. Okay? And just to give you a reminder, in core collapse supernova, we expect that the core of a massive star, which is made of iron 56, cannot generate any more energy by nuclear burning, eventually becomes unstable, reaches a Chandrasekhar mass, and collapses. And so if everything goes well in the supernova mechanism, we make a proto-neutron star that starts irradiating its surroundings with neutrinos, and a small fraction of those neutrinos are going to be absorbed and ideally launch a shock and explode the supernova. Okay? That's the classic neutrino mechanism. In a small fraction of those supernovae, we expect that rotation is important, and we might have a magnetorotational core collapse supernova. Recent simulations show that the jet actually has a hard time coming out in the classical sense when you model the problem in 3D, but it's still a feasible mechanism. But we expect most supernova to explode. If they explode, they should explode via this mechanism. Okay? But there are cases, of course, in which this mechanism will fail. Okay? The shock is just not going to be revived. Okay? And in that case, accretion will continue until the proto-neutron star will exceed the maximum mass that can be supported by the dense matter equation of state, and it will collapse to a black hole. Okay? And once collapse to a black hole begins, then everything goes into the black hole, and in principle, that should be the end of it. Okay? If nothing else happens, just the star is swallowed completely.
Is there always guaranteed to collapse just one black hole?
You think that it could be split into two?
No, can you get a constraint from the equation of state that the neutron star can't, well, is it possible for a neutron star to support enough angular momentum such that it can't collapse to just one black hole?
I mean, from neutron star mergers, I mean, those are the most rapidly rotating cases we see. Basically, breakup rotation, you always get one black hole, actually. I mean, the black hole can have all the spin. I mean, you want basically all the way to maximal spinning. So as far as I know, nobody has seen two black holes, for example, forming out of a hypermassive neutron star. But this is nowhere near rapidly rotating as a neutron star merger, for example. It's much less angular momentum. Okay. Now, if the star is rotating, but now not like a merger, but still rotating rapidly compared to most stars, then you could possibly form an accretion disk around this black hole. Okay. And depending on the value of that angular momentum, circularization will happen at a radius such that you can have this neutrino-cooled accretion disk and maybe launch a long GRB via the classical collapsor mechanism, and maybe even a broad light type 1c supernova. Okay? And that's been known for a while. But if there's little rotation, in principle, everything should go into the black hole. Okay? That's kind of the naive view of it. But of course, the story is slightly more complicated, and luckily there's more happening. So except if we are in an extreme massive range above, I don't know, 150 solar masses or 200 solar masses, where you have a peri-instability supernova, for all stars below that, we always have a proto-neutron star phase before forming the black hole. Okay, you never collapse to a black hole right away. Okay, and that during that proto-neutron star phase, a sum of the mass energy of the proto-neutron star is radiated away. Okay, in such a way that the gravitational mass becomes smaller than the baryonic mass. Okay, and this effect was first identified by Nariosin in 1980. What that means is that the outer layers of the star feel that the acceleration of gravity drops because a little bit of the mass was lost to neutrinos. Okay? The mass energy was lost to neutrinos. And so when you were in hydrostatic equilibrium and suddenly the gravity is smaller, you have an excess of pressure, and the star just launches a pressure wave. Okay?
I'm confused about the principle of this. I thought I understood this, but now I'm not sure. If you have say a 20 solar mass star, and
Yeah.
you lose 0.1 solar masses
Yes.
to neutrinos,
Yes.
okay, with a 19.9 solar mass star, that corresponds to a small radial displacement from hydrostatic equilibrium in the outer parts.
It's a sound pulse that everywhere.
So you're saying that the sound pulse steepens and then...
Yeah, I'll show the results. Okay. So but just to have a better sense of the physics. Okay. So the gravitational mass is not lost instantaneously everywhere, but there's a finite time scale over which these neutrinos are emitted, and so we lose the gravitational mass over a certain time scale, and has a magnitude. Let's call it delta mg, change in gravitational mass, and it turns out that if you're far enough away, that change is going to be very quick, so it's instantaneous change in the gravity. But if you're very close to the center, it's going to be slow. Okay, that's intuitively what the limiting cases are. But now, if you want to see where the transition is, one can consider the free fall time, which is the time scale over which matter will respond to a change in gravity. Okay, and there's a radius. Okay, outside of which the free fall time is longer than the neutrino cooling time. Okay, meaning that the time it takes for this material to fall to the black hole, okay, or to begin falling to the black hole is longer than the time it takes for the gravity to change. And so it feels this outward pressure gradient, whereas if it's closer to the black hole, so the free fall time is very short, no matter how much gravitational mass you lose, you just go into the black hole. Okay, and there's a characteristic radius where this happens. Okay, and one can estimate the energy imparted to a shell by a change in gravity. So we have this delta mg, okay, change of gravitational mass, the acceleration of gravity changes by g and delta mg over r squared. Okay, that's the change in gravity. And with that little change in gravity, if we multiply by the free fall time, which is the time scale over which matter responds, we get a velocity, okay, an impulse over the free fall time. I can call it little v. Okay? And if we multiply that little v by the mass of a shell in the star, we get a characteristic change in the energy of that mass shell. Okay? If we do the numbers, it works out to be quadratic on the change in the gravitational mass, and depends on the radius where you are in the gravitational field. And plugging in the numbers is about 10 to the 48 ergs of energy. Okay? What this shows here is this energy as a function of the free fall time, which, as we saw before, is dependent on the radius and the enclosed mass, so you can use it as a proxy for the radial coordinate because it's monotonic. And basically, we have three cases. Red supergiant, that's a massive star with a convective envelope and shell burning. Blue supergiant, it's a radiative envelope and shell burning. And then a Wolf-Rayet star, which has lost all the outer layers by stellar wind. It's much more compact. And in all cases, this energy impulse grows as a function of radius until this characteristic radius I told you before, where this free fall time is equal to a fiducial neutrino cooling time of a few seconds. Okay? And then it's about constant. It depends on the properties of the mass enclosed inside the radius. This is about the edge of the iron core. Okay? So this is the characteristic energy one can impart to the star in this way. And one can estimate the amount of mass that is ejected if one were to inject this energy in the star. If we look at the exterior mass, okay, the outer layers, and the binding energy. Okay, this is internal minus gravitational, or plus gravitational. Okay, and so these are the numbers one get when we're using the maximum value we get from the energy release. And for a red supergiant, we expect that about a few solar masses should be unbound by this mechanism. Blue supergiant, a few tenths of a solar mass, and Wolf-Rayet, very compact, a few thousandths of a solar mass.
There's no transfer just into heat or anything like that. You use all the energy you manage to use.
Yes, so it's the upper limit. So the 100% efficiency. Okay, and we will see that it's not too bad an approximation. And I'm almost out of time, but I'll just try to quickly go through it. Now, this mechanism has been shown to work with simulations in the case of a red supergiant, very extended star. It's the easiest case because the envelope of a red supergiant is very loosely bound, so any energy you inject is going to inject some mass. Okay, and by Lobrom and Woosley, I forgot here to put Stan Woosley, they found that this ejects a shell of a few solar masses with an energy of about 10 to the 39 ergs, leading to a transient that lasts about 1 year and peaks in the infrared, 3,000 Kelvin. Tony Powder showed that the shock breakout is more likely to be detected. It's a few days and peaks in the optical. Okay, and this is a candidate event coming out of the Large Binocular Telescope survey of disappearing stars. So they look at the sky, they look for red supergiants, and they try to find cases in which the star goes away. And this is a red supergiant that had this luminosity of 10 to the 5 solar luminosities, had a transient lasting for a year, and then it went down below its previous brightness level. So this is a candidate for this type of mechanism, and they call it BH1 for black hole 1. Okay? That's the idea. And then the infrared emission continues, and it has a slope that is consistent with accretion from a fallback disk. Okay? T to the minus 4/3.
What was the mass of the projector before the collapse?
I believe it's 25 solar masses. I believe it could be 15, but I just don't remember exactly. So the mechanism is very generic. It's not exclusive to red supergiants. So we set out to explore this in a wider range of progenitors, and we use flash in 1D. Again, hydro equations, and we excise the inner core and evolve it as a point mass, and then we pretend that it radiates neutrinos with some analytic prescription. And we remove the inner boundary at subsequent times so that we save all this CFL current restriction of the time step at very small radius, because the velocity is supersonic increasingly, and it doesn't do anything to the outer parts of the domain, so we just take it away. And we are able to follow the shock propagation over the entire star. Okay? Red supergiant, blue supergiant, Wolf-Rayet stars. Okay? This is the shock velocity, or the sound wave turning into shock velocity, the Mach number, the density, and the temperature. Okay? So a few things to pay attention to. This is the radius I told you before, where the neutrino cooling time is equal to the free fall time. So we see that the sound pulse, okay, emerges from this radius, and is initially subsonic, and it steepens into a shock, but the shock is not very energetic. It's just Mach number 1, okay, at the most. And only when it reaches the surface, it accelerates, and it can get, depending on the compactness of the star, to a few thousand to tens of thousands of kilometers per second. Okay. And the energies, this is the kinetic energy of the shell, and this is the maximum energy I showed you before. One can estimate analytically is always a factor of a few above. Okay, means that the efficiency is not perfect. And it depends whether you have a red supergiant, blue supergiant, or Wolf-Rayet, how much mass you eject, how much fallback there is. Okay, fallback meaning that you start with a large mass in the sound pulse, but it's lost. Okay, it's a function of time. So this is the mass enclosed in this pulse that's moving out, just because a component of it is gravitationally bound. So it's just going to keep going all the way and just falls back, and you are left only with the gravitationally unbound component. Okay, so it's energy, this is mass, and this is velocity. I'm going a bit too fast because I'm almost out of time. But the point I want to make is that you can eject mass no matter what the progenitor. Okay, it's just that the amounts and the velocities are different for each of them. Of course, there are cases in which no mass is ejected because the envelope is too large and the compactness of the core is too large. And so when the sound pulse gets to the surface, it doesn't eject anything, and just the star goes to the black hole. Okay? Nothing happens. But one can plot correlations between the core compactness. So this is m/r of the inner regions in units that supernova theorists like to use, and then m/r of the outer envelope of the star, which also tells you the strength of the gravitational field. Okay? And so two things: the energy of the ejecta correlates well with the compactness of the core, so that's the region where we're launching this sound pulse, and the mass ejected correlates with the envelope compactness. And again, this has to do with the binding energy of the exterior shells of the star. Okay? And these are the transients. given the velocity, the mass, we can go back to this argument I told you about at the very beginning of the talk and compute luminosities of shock breakout, velocities, temperatures at breakout, and luminosities and times of the plateau phase. Okay, when the recombination front is coming in and all the photons are streaming from a photosphere. So we recover the previous results for a red supergiant. So the transient lasts for about a year at almost 10 to the 6 solar luminosities in the infrared. The shock breakouts, a few days in the optical or UV. Interestingly, the blue supergiant, okay, this has never been done before. It's an interesting case. Shock breakout a few hours, and plateau emission is 20 days, 10 to the 6 solar luminosities. That's about 10 to the 40 ergs per second. And the Wolf-Rayet, of course, is very short. The shock breakout is set by the light crossing time. The plateau is even fainter than the star, so it's not really interesting. But here we are pretending for now that the exterior of the star is empty, when in reality a Wolf-Rayet star has a dense wind that will affect how this shock breakout happens. So these numbers may not be entirely reliable, but just give us a sense for the scale.
Well, how much mass must it be? Because the wind velocity will only affect the optical depth of the wind is larger than the optical depth at breakout.
Yes.
So the optical depth, normally supernovae is about like 30.
Yeah.
How much mass do you need?
I didn't work out that number, but it's a very small amount of mass, like 10 to the -4, 10 to -3 solar masses. So it might not be that that large or, compared to the wind. Yeah, we didn't even put the wind profile outside, but it might be just a simple solution.
What happened to the star actually?
It's gone.
It's gone because most of the envelopes are bound. I thought you only bound.
Just a little bit. And the rest just falls in. So the outermost few solar masses make it out, and the remaining 10 or so just go into the black hole. So you end up with a 10 solar mass black hole plus a few solar masses.
Radio info.
Yeah.
That's just rotated very slowly. Not to be stopped by the centrifugal barrier.
Yeah. Sorry. Yeah, I should say that all these calculations assume that there's no rotation. Okay. In reality, of course, there's going to be certain radius at which the angular momentum you had at the outer layers is going to, like an outburst. Well, I think that's the basis of the claim that this late infrared decline, which is t to the -4/3, is given by a fallback disk. That's the time dependence you expect when you have basically a relatively inefficient disk at large radius evolving for a long time.
You think it's a complete optical effect? You can't see the inner visual.
Not necessarily. I mean, once the transient fades, then you. Yeah. So this is what they're claiming. Okay. Yeah, because it's cold.
But it's likely to eject more mass than the process you're calculating.
You mean the disk, like a jet? You mean?
Yeah.
Okay.
That will train more material.
Yes. So we haven't gotten to that point yet, but it's possible. Yeah. I see what you mean. I don't know if. First, I don't know if they looked at this in high energy, and B, I don't know if it will be bright enough to be detected. But it's certainly possible that, and we're not seeing it. Yes, so that's an interesting homework problem, I would say. And I think I'm out of time, so I will leave it at that. And if there are any questions, I'm happy to answer. Thank you.
How does the last method that you showed, how does the timescale for mass loss compare with the timescale for the shock to lose causal contact in the center?
You mean gravitational mass loss?
Yes. The result of neutrino emission.
Oh yeah. So our fiducial timescale here is 3 seconds, and so 3 seconds is basically the timescale over which you launch this, and then it's gone, and mass loss stops after that.
When do you lose causal contact?
Causal contact, you mean become supersonic? All of this pretty much is supersonic after like a second or so. So you mean no matter what you do at the inner boundary or like the black hole?
My point is that the shock the shock that breaks up only knows about the energy that was released until it lost causal contact. All the energy afterward, it's
Yes.
oblivious to it.
So yeah, so basically,
Not if something comes back to you is much faster. You can catch
Right.
up. And it probably is much faster. Which is not in the domain of this spherical calculation. I think, for the Wolf-Rayet star or even the blue supergiant, you may well be on fairly solid grounds. It's nice. Blue supergiant will lost a lot of mass to the wind, and will be slowed down significantly by that.
yeah,
And relatively shallow convective layer. And Wolf-Rayet star, of course, is very compact, so in isolation, which it probably isn't, of course, binarity will change all of this.
yeah, exactly.
In isolation, it's not likely to have any material that would become perfectly supported
Yeah,
before it hits the black hole.
yeah,
But red supergiant is another matter.
yeah, I know. Yeah, it's much more complex.
Exactly.
Yeah,
Exactly.
yeah, yeah. So, yes, go ahead.
I also don't see why it's going to fall, the remaining star is going to fall in. It's still got pressure support.
That's just moving out, right?
No, that's a material which is
Well, because
Course.
once you remove the inner boundary, so pressure waves don't go out. Once the flow becomes supersonic, and so there's to have hydrostatic equilibrium.
in the middle.
Oh, it's just a vacuum cleaner, yeah.
But still, the pressure support which takes some time.
It's a pressure wave that goes out, a rarefaction wave that communicates to the outer layers that the support is being removed from underneath. And so, and we found that, so if you mark as the edge of the shell being the point of zero velocity, that pretty much moves at this local sound speed. Okay, so this is the local sound speed, the black curve. Okay, and the red is the lower edge of this shell. It goes pretty much at the sound speed, communicating to the star that hey, we lost support.